Hello, 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 Yaneli. Hello, Vanita. Hello, Annie. Hello, Chastity. Hello, chat. Wait. Good afternoon, Yaneli. Good afternoon, Kaya. Good afternoon, Vanita. Good afternoon, Natalie. Natalie. Good afternoon, Ariana. Good afternoon, Genesis. Good afternoon, Carlos. Good afternoon, Chastity. Good afternoon, Brian. Good afternoon, Annie. Good afternoon, Mariam. Good afternoon, Sydney. All right. Yes, good afternoon. Indeed. All right, let's get rolling. Let's get rolling. What does that mean? It means Oh, it doesn't mean that. Well, it sort of means that. Hold on. It sort of means this. Well, it means this, but it really means so the second equation. Okay, very quickly. The second equation is the goal of this week, not necessarily or at all the goal of today. The second equation is what we need to develop as we transition from these oscillators to collections of oscillators as we transition from one harmonic oscillator to a multiplicity of properly phase staggered oscillators, which ultimately makes a wave. That is the goal. And that goal will particularly, and that's, in other words, we're doing all this oscillation stuff to ultimately to construct and observe unthingy things such as wave pulses. And you will begin to see that in lab 3 and 4, which I gather you are just about to begin. Yes, I gather you're just beginning lab 3, which is perfect. So we want to start preparing you. We want to get, we want to turn these harmonic oscillators into waves. That's the bottom line. Uh, and that's where that second equation on the board comes into play. However, I kind of want to blast through the rest of homework 2 and 3 in order to get us there. So that's exact. So what I'm going to do today is that try to put to bed homework 2 at least because it was so long. Um, and then homework 3 is very short. So let's do that. One thing, somebody in the other class noticed that I had a mistake with regard to the deadlines for homework 4 and 5. Like they were but it's fixed now. So homework 4 is due a week from this Wednesday, and you really should not even, I mean, you can't. There's no expectation that you would start it yet because the context for it has not been explained at all. And even what the question means has not even been explained at all. It'll be a lot easier to picture how to do homework 4 once we get into that stuff in the classes and once you've begun lab 3. So hopefully, this week is a little bit of time for me to catch up with you and you to catch up with yourselves and revise and upload homework 2 and 3. And if you notice that homework 5 looked like it was due before homework 4, you were correct, but that's been corrected. So the very next thing that's due is a week from this Wednesday. Okay. That said, yes, and good afternoon and hi to direct chat person. Okay. That said, I want to go, I'm going to screen, I want to go back to homework 2. I want to finish homework 2 today. Um, and I think for the sake of I'm going to do a quick. I'm going to go back and forth between the screens just to be totally clear in case you're watching this later or in case we've forgotten where we are. Like this is where we are right now. Or well, this homework is where we are right now. Um, and we got as far as F and G. We got to F and G last class. We spent a long time on F and G, not because they're so hard to do. They're not, I hope. But because the implication of F and G is sort of large, the implication of F and G that you're seeing on the board right now is that whereas we thought that the cosine solution is the way to describe a simple harmonic oscillator, i.e., we thought the cosine solution was the solution to the differential equation for simple harmonic oscillation. What we found in F and G is that that cosine solution, x naught cosine omega t, or something to that effect, that cosine solution is a solution. If by cosine omega t we tacitly mean cosine omega t plus 0, then that is a solution to the differential equation that we're dealing with, i.e., it is a way to describe and predict the motion of a simple harmonic oscillator, right? But it turns out that in F, with this arbitrary example of the number 3.5 being added to the parentheses, we find out, wait a second, omega t plus 0 is a way, but it's not the only way to describe an oscillator. You could throw in a constant measured in radians into the cosine argument, and you're still describing an oscillator. So it turns out any number can be thrown in there, and that number must mean something physically. It means what we now know as the phase constant. That number inside the cosine parentheses tells you the head start or the delay that some oscillator has with regard to its cycle. Like if that number in there is 0, if it's omega t plus 0, that tacitly means that we started our stopwatch exactly at the moment that the oscillator was at an amplitude position, the positive amplitude position. But if, for example, that phase constant is like pi over 2 radians, that would mean that when we started our stopwatch, the oscillator was already pi over 2 radians into its cycle, i.e., a quarter of the way into its cycle, because the cycle is 2 pi radians. So it was already a quarter of the way into its cycle. So the stopwatch, so if there's a phase constant of pi over 2 radians, we didn't start our stopwatch when the oscillator was at amplitude. We started it when the oscillator was already at equilibrium in that example, right? So we found out that there's this extra term that we can and should keep track of that tells us at what stage of the cycle, at what phase an oscillator is when we start making measurements, when we start timing it, right? And I'm just reviewing as usual, like what the point of F, like this is the whole discovery of F and G really is that, yes, even a cosine solution with a phase constant tucked in will be a solution to the differential equation that describes harmonic oscillation. Therefore, we should keep track of the phase constant. And then I say, physically, if you're still with me, you might say, okay, that's all fine. Like I see that the math works, but like, why would we ever bother? Why would we ever do something as inconvenient as starting our stopwatch anywhere but the most obvious place, the place where the thing is slowed all the way down to 0 and is about to turn around and come back? Like, why would we not ever just start? Why would we not always just start our stopwatch there and avoid all of this nonsense? And we would listen to you. It's a very good point, whoever you are that is thinking that right now. We would like to just start our stopwatch as you did in lab 1 and 2. We would like to start our stopwatch at the moment that the oscillator has slowed down to nothing and is about to turn around and come back. Like that's the easiest place to track it, and it's the easiest math. But so we will do that as long as we only have one oscillator to track. But the moment we have a bunch of oscillators at different places of their phase, at different phases of their cycles, then we can't do that for all of them anymore. And again, that's where this ship is heading. We're doing all of this math and all of this analysis is on this key ingredient so that we can put this ingredient, so that we can replicate this ingredient, this oscillator, and put a bunch of them next to each other and stagger their phases deliberately so that they're all going up and down and up and down and up and down, like in a rhythm. And again, if you're with me right now, you might already be picturing if you had a bunch of oscillators going up and down and up and down, up and down, all in succession, but all at different and properly organized points in their cycles, what you would create is a ripple, a pulse, known as a wave. And so that's like the point of all of this. That's where we're going. That's where you're going in lab 3. That's where the math is going. So in order for the math to get us there and everything to get us there, we need to be able to track oscillators that have varying phase constants. Okay, that is the takeaway from F and G. So then we got to H. Sorry, am I still on the screen? Wait, something's in the chat. Sorry. Let me look in the chat. Oh, sorry. Let me first go falsetto. Oh, oh, wait, yeah, I'm looking in the chat. I'm sorry. I thought we said that. Maybe, yeah. So I'm just looking at the chat. The question in the chat is like, what units would the 3.5 be in part F? And the answer is definitely, I mean, it's a great question, except I'm like mortified if I didn't already say this. The 3.5 in part F definitely is in units of radians. I mean, and so any phase constant that we put there must be in units of radians, uh, like no matter what. I think this answers the question. I mean, because it's being added to an omega t, and omega t has to be in radians because omega deliberately in the first place was in radians per second in order to cancel out the seconds embedded in the t, right? So you can only add radians to other radians, and together the entire parenthesis then makes radians, and that's good because that's the only thing we could take a cosine of. Hopefully that makes sense. I think, or let me know if it didn't answer the question, or what I think, or let me know. Okay, I'm gonna keep right. So phase constant is always measured in radian. Oh, chat. Sorry. Okay, I'm going back and forth between screens. I'm just seeing it. Yes, good. Thank you so much. I appreciate that. I like that helps me. As you know. Okay. So right. So that's F and G. But then we got to H. Now, to be honest, I'm not 100% sure whether I remember. I think I very quickly, right at the end of last class, I think we very quickly discussed H. So I'm going to sort of, again, somewhat quickly discuss H now and then move to I and J. H on the screen. The reason suddenly we're talking about exponentials in H is because in F and G, we realized that this cosine the cosine omega t thing, which we started to get used to a couple weeks ago, the cosine omega t, to say that it is a solution to the differential equation is the mathematical way of saying it is a way to describe and predict a simple harmonic oscillator. Right? Okay, but what we discovered in F and G is that the cosine omega t is not the only way. It's a way. Cosine omega t plus phi is the more general way. But once we realize that, you see, once we realize, wait a minute, we could throw in a phi, a phase constant, into the parentheses, and like we're still talking about harmonic oscillators when we do that. And in fact, we're talking about them in a sort of better way. I mean, in a more informative way. Then we realize, oh, so wait a minute, does the buck stop there? I mean, once we're realizing that we could use cosines, and especially if we could do cosine plus a phase, doesn't that mean, or didn't some people in this class like already even suggest that if we were careful enough, we could use sine as well? And yes, and people have already said that, and I'm agreeing, and I'm agreeing. If you could use cosine, you could use sine, but the reason I didn't like sine originally, or the reason that it's not my first instinct, the reason cosine's more convenient for the physics, as we discussed, is that cosine is phased properly. Like the very first value of cosine, the 0th value of cosine is non-zero, right? Which in other words, when the oscillator, when it describes the physics I'm saying, which is that when we start our stopwatch, we like to believe the oscillator is somewhere other than equilibrium. Otherwise, like, why would it move at all? But now you realize, wait, if we're allowed to throw a phase constant in there, if we're allowed to put a phase constant in cosine and adjust it, is it I mean, isn't throwing a phase constant of pi over 2 sort of equivalent? I mean, to shifting the whole graph, the whole cosine graph by pi over 2 radians? And isn't that just like make it a sine graph? Which brings it back to the students in this class who originally said, wait, like, okay, couldn't we use a sine? Well, yes. So, right, especially if you're willing to take into account phase constants, you could talk cosine or you could talk sine. And the reason both, right? So we're realizing, wait a minute, there's not just necessarily one way of doing this. So then we say, wait, what was it about cosine and sine in the first place that even made them come to our mind? Like, why are we like, why are we talking about trigonometric functions to describe something that's going back and forth? And remember, we said a couple of things. Well, number one, trigonometric functions deal with circles, and the math of circles is really convenient for the physics of cycles. I mean, that's number one. But then number two, also remember the reason that cosines and sines are coming up, especially when we're thinking in terms of differential equations, is that cosines and sines have that property that when you take derivatives of them, eventually you get back to themselves, which is what we want. The differential equation, all differential equations, in fact, are demanding some kind of feedback function, right? Because they're describing a feedback behavior. Remember, please, that this differential equation, the one that's sitting there right there, like in G and in I, like the differential equation that's sitting there in the screen right now, the differential equation is saying that the second time derivative of x is equal to the negative times a constant times x itself. That's what the math is saying. In English, what that's saying is this all came from the fact that we had an object whose position we wanted to predict in time. And we always know in physics, position, in order to predict position in time, you always need acceleration. Always in physics. Like that's the way you predict where something is. You predict the rate at which it's going to change, the rate at which it's going to move, right? So you always need acceleration in order to predict position. But in this case of the oscillator, I say, what's the position? You say, I need the acceleration. What's the acceleration doing? And then I say, well, it depends on the position. Like literally, right? That feedback aspect of the motion, that while position depends on acceleration as it always does, the acceleration itself depends on position. That's what the differential equation is saying. The rate of change of position with respect to time depends on position. That's cray, yo. Like really, that's why we're spending so much time on it. It's an interesting, bizarre phenomenon that if I didn't know better, I would not think could even be solved. But so where am I going with this? Where I'm going is that's why we're trying mathematical functions that actually describe that type of self-reference. Cosine, the rate at which cosine changes the rate at which cosine changes is sine. Like literally, that's what, or negative sine, really. But right when you say, what's the derivative of sine? Oh, the derivative of sine is cosine. Think about what you're really saying is the velocity of sine is cosine. The rate at which, and the velocity of that is back to sine, like with a negative sign. I'm not trying to confuse you. I'm trying to point out this is the sort of, it's like the math is confusing in exactly the same way that the physics is confusing. I mean, if it is confusing to you. And the confusing nature is that it loops back on itself. So it is the appropriate math to describe. It's like unbelievable that we have math to describe such a loopy kind of thing. So we tried cosines and sines because they do that. Because if you take enough derivatives, when you take derivatives of cosines, you eventually get back to cosines with a negative sign, which is what we want. So then we thought, so now finally going to H, I'm just, when we get back to H, it's where it's going, oh, well, if we're like allowed to broaden our horizons and think of other functions, can we think of other functions that do that? Oh, E does that. In fact, E to the X, E to the Y. And I think I wrote this, I'm going to assume that I did write this on Wednesday. Stop me if I didn't, but I think we said, like, if you know that the kernel function, the pure Platonic form of the function that literally does the thing I just described, the name of the function whose rate of change is literally itself, is the exponential function. Again, now, and again, that is a mouthful. You might say, like, why does the exponential function do that? I would say put it the other way around in your mind. Something does that in nature. So there's got to be a name for it. The name for it is exponential function. What do you mean something does that in nature? Well, it comes up a lot. You know this. Again, why are exponential functions always used to describe continuous compounding of interest, right? That's like the classic example that comes up in math classes that we all just memorize, blah, blah, blah. Because continuous compound of interest is exactly that idea. You walk into the bank account, you say, how much money is in my account? They say, depends on how much interest we added in the past. You say, well, how much interest did you add in the past? They say, depends how much is in your account, right? Like literally, that's what exponential relation means. So we decide in H, let's freaking like try exponential. So, I mean, it means it means if y equals e to the x, then dy dx is e to the x. The rate at which the darn thing changes is the darn thing itself. That is the essence of feedback. That's what we have going on here with position and acceleration in an oscillator. So we decide in H, whether it's as being scientists who are experimenting or as mathematicians who are contemplating, in H, we say, hey, can we try an exponential function? Could that like work? And we take two derivatives of it in H. Again, this is where I think we left off class ago, and stop me if I'm wrong. We take two derivatives of it, and we use the chain rule. And so the negative omega comes out from chain rule, but it comes out twice. So what we get, and I think you wrote this down, what we get in H sub 2, like the second derivative of x with respect to t, what we get is omega squared e to the negative omega t. Like negative omega comes out from chain rule, but then it comes out again. So you get omega squared, but the negatives, like you get a negative times a negative, which equals a positive. So you get omega squared e to the negative t, e to the negative omega t. So then when you go to question I that's on the board here, and again, I believe we wrote these answers down. I hope we did. When you get to I, you know, the answer you get looks darn close to the right side of that differential equation. Darn close, but not close enough. What you get in H is you get d2x dt squared equals positive omega squared x. So when we're asked, so does this solve that differential equation? We say, no, it does not. It solves a differential equation. It is the solution to a differential equation, but not the one that we're focused on, not the one that we care about right now as physicists. It solves some differential equation, but not one that has a negative sign in it. And if you ask, does the negative sign really make that much of a big difference? Are we really getting like our knickers in a twist over a negative sign? Oh, yes, we are. Because that negative sign is the negative sign from f equals negative kx. That negative sign that's in our differential equation is the negative sign from Hooke's law. The negative sign means that the position is continually being restored to equilibrium. That if the position's on the right, then we get pulled to the left. If we're on the left, we get pulled to the right. And furthermore, now that we've done all of our homework one and answer all those questions, it's not even just the position, if you think about it. It's all the derivatives with the whole thing of oscillation. When you're washing back and forth, back and forth, back and forth as an oscillator, what's fascinating, among many other things, is not just that you keep in your position going there and back and there and back, but that your velocities, your first derivatives, Your velocities are to the left and then heading to the right and then heading to the left, and they're positive and then they're negative. Right? Whichever side you're on, you're heading the other way. So your velocities are like the opposite of your positions at any time, and flip-flopping and your accelerations are doing the same thing, and your jerks are doing the same thing, and your whips are doing this, right? Like the whole thing about an oscillator is amazing. It's super simple, but it is so richly layered. Every single derivative is flipping back and forth and flipping back and forth, and in the opposite way from the derivative before it, if you're following me. All of that oscillation, that continually differentiated oscillation, is captured by and ensured by the negative sign. So when we tried the exponential function, it was a good try, it was a good thought, but it didn't work out because it didn't produce the negative sign. And by the way, is that a shocker? Maybe it's not a shocker because exponential functions like go like this, or they go like this, or like exponential functions are monotonic. They just grow and grow and grow, or they decay and decay and decay. So in some ways, the fact that the exponential didn't work out, in some ways, it's like, oh, okay, yeah. I guess it was a nice try, but like we are looking for a function that wiggles, cycles somehow, and exponential functions don't seem to do that. So I guess it's okay. I'm almost done. I always say that. I'm saying the answer to I was no because it didn't produce a negative sign appropriately. So I'm going to go on in a minute. But why do we go on to the answer was no. But then you might say, if you're still with me, you might look at H and you might go, well, it didn't work because you like jammed that because you put a negative sign in there in the exponent. Like, why'd you do that, Yaverbaum? Like, and maybe I did it because like I was hoping to get a negative sign. So I stuck a negative sign in the exponent. But you might say, if you're still with me, you might say, well, that's where you got yourself into trouble because like the negatives canceled themselves out. So you ended up with no negative. So don't do that next time. Like don't overreach, Yaverbaum. So what you might do if you want to be a scientist about it, or if you're getting bored of hearing the sound of my voice as I am, you might just on a piece of paper right now try what if, or if this were an exam, I might, switch things up a little bit. You might say, what if X equals e to the positive omega t? Maybe that will work. I mean, the negative didn't work. It produced a positive. Maybe a positive will produce a negative. If two wrongs don't produce a right, maybe two rights will produce an airplane. What? Or, whatever. So you try that. But look, and hopefully you are trying that, but if you try that, X equals e to the omega t, you take one derivative, you do chain rule, you'll get omega e equals e to the omega t. You do a second derivative with chain rule again, and you'll now get two positives equaling a positive. You're still going to have the same problem. I'm not saying it's a wrong thing, but I'm saying no matter whether I put a negative or I don't get a negative out in front of the whole thing. It doesn't seem to be harmonic oscillation. So then I go, oh, yeah, right. This is like that old problem from fifth grade or whatever. It's like that whenever you first learned about squares and squared roots, not fifth grade, whatever. It's like that problem of like, wait a minute, a negative times a negative equals a positive, and a positive times a positive equals a positive. So like, how can I take a number and multiply it by itself and somehow get a negative? Like what, in other words, what if are there any, because the only way to get a negative, it seems like, is to multiply a negative by a positive. So if I'm trying to square something as the chain rule and as second derivatives force me to do, if I'm trying to square something, how the heck can I square something and get a negative, right? And that's like what's the square root of a negative number such as -1? And that's where we invent or discover this whole concept of imaginary numbers. So if we move to J now, what I'm trying to say at 1,000,000 miles an hour in the top of my lungs, what I'm trying to say is first of all, if when you looked at H, you were like, what? When did exponentials come into this class? I'm trying to explain why they just came in, because they related to cosines in that they are infinitely differentiable. But then if you looked at, but exponential did not seem to do what we need a mathematical function here to do in physics. Didn't seem to. But then if you go to J and you're like, what? I equals a negative. I mean, I equals the square root of -1. Like, what is happening in this class? Why suddenly am I now dealing with imaginary numbers in a freaking supposedly real science class? I mean, fair question. The answer is, first of all, as I'm sure you've heard, imaginary is a bad term for those kind of numbers. Like, I mean, sure, they're imaginary in the sense that they're in our head, but that's true of all numbers. They are, I'm sure you've heard, it's better to call them complex numbers. They're not anymore, they're useful and real. And it turns out they're not just useful and real when you're sitting around counting quantities, but when you're literally trying to analyze the physical world. It turns out complex numbers are worth considering. What do you need to know about because I'm looking for a number here. I'm looking for a way for something to square itself and still generate a negative number. I mean, it looks like complex numbers are the way to go. If you're asking yourself, wait a minute, I have to understand complex numbers to do this? Like, do I have to have taken a class, or like, what do I need to know or remember about complex numbers in order to do any of this stuff? All you need to know is exactly what's written on the sheet, that the definition of the imaginary number is the square root of -1. Like, that is what I is. Everything else that we need to know follows from that. So I'm going to try. So I'm going to try an exponential function with an imaginary constant. Whoa! In the hopes that that might somehow weirdly produce derivatives that actually adequately describe the harmonic oscillator. That is what's happening in J. That is what I'm going to do, right? Okay. And that's why, like, it's not. And again, like, did I expect you to think about all that or know all of that when you were doing this homework? No, not at all. What I'm trying to get across is, like, believe me, like, we want to get more and more used to the fact that every next step in physics, that we may not see how it's motivated right away, or we may not see right away how it follows from the last step, but it is, and it gets easier and easier to see how things are all connected if you start having faith that they are in fact connected. Like, honestly, you will see the connections on your own more and more if you go in with the belief that there is a connection to be seen. Just saying. So I'm going to switch screens. I'm going to go to J now. So this, but also, I'm sorry. A side note: in order to have the faith that things are connected, whatever, you'll also support that faith. You don't have to see the connection in order to do things. Like you just have to have the faith that you're going to be okay and not be hurt. I'm saying, I'm just trying to give a context now for why J even makes sense as a question, but I'm also saying, like, it doesn't have to make sense as the next question for you to do it. You just have to literally accept the premises that it's providing, which is that I is the name for the square root of -1. If we accept that, then I'm going to switch screens. Am I going to switch screens? I'm going to switch screens. Wait, am I? Yes, I am. Wait, am I?
Wait, Professor,
Oh, yeah, sorry. Yeah. Oh, did I just lose? It was, sorry. Yes, yes.
you kind of mentioned that like uh you mentioned like how complex numbers are like very applicable to like what we're studying right now, like the physical world. And you kind of like forgot to explain it. Can I ask you to like explain like
Oh,
finish your thought? Because I'm like curious.
oh, wait, no. I'm glad you're curious. And it's not that I just forgot to be a human being. No, I didn't forget. Like, that's what I'm about to do right now, I guess is what I'm saying. Like, I know I would totally, I'm glad you're curious. I will totally address that. But give me 2 minutes. Like, yes, I mean, I forgot to make it clear what the order is and what I'm saying things. Um, Bear with me for a second. Yes, I'm totally going to explain that. It's like, so here's what I'm saying. Great question. Here's what I'm saying to everybody. If you accept that I is the square root of -1, and what that means is it's a number. It's a number that doesn't change. It may be an interesting special number that I'm going to like expand on in a minute, but it's just a number, i.e., it's a constant. So any of our rules about derivatives still apply as always, and we just treat I like any other number, like 4 or A or B or whatever. So if I want, so if I'm given the function x equals e to the I omega t, if I take the derivative of it, I recognize that e to the x is always the derivative, the dy dx is always e to the x, and I do chain rule. So to do one derivative, I mean, yeah, it's written here on the board. Yeah, I take the I and the omega out, and I get dx dt equals I omega e to the I omega t, right? And then to take the second derivative, I do it again. So I take the I omega out again. So then I get I squared omega squared e to the I omega t. But then here's the key. I mean, sort of the key to, well, the key is that if I is the square root of -1, then by definition, I squared is -1, right? I mean, and that's not a leap. Like that's like the point of it. So when I just got that the second derivative is I squared omega squared e to the I omega t, what I'm really getting is I'm getting -1 times omega squared e to the I omega t, which was the whole reason that I even thought to introduce I in the first place, because I is that thing where you can square it and get a negative number. So there's my negative sign there. And so, oh, and so to be explicit, like since this piece right here was what I was conjecturing to be x, it seems that if you make x that, then you do have a solution to the differential equation. So this is almost the answer to Annie's question, like almost. Um, so x, so wait, so x equals e to the omega t was like a nice thought mathematically, but did not work. It did not produce the negative sign. And then we said, well, maybe that's not even that big of a surprise because like there was some reason to hope that it would work. But then upon reflection, exponential functions don't wiggle. So why would it describe a wiggling system? But then apparently if we throw a complex constant into the exponential, then apparently it does satisfy the differential equation, and it does therefore describe a simple harmonic oscillator. And by the way, that would have worked whether or not if we had said e to the I omega t or e to the negative I omega t, either one would work. If you just check the math, you'll see. So it turns out now here's where I think is the answer to Andy's question. Like that shows that anything that we wanted to describe in physics, in the physical, natural, real world, anything that we want to describe with cosines or sines, in fact, we could describe with exponentials as long as they are complex exponentials. In other words, I, the imaginary number, and everything that you've ever heard about it, or a plus bi, and the complex plane of all those numbers that involve imaginary parts, that it turns out to be super applicable to the physical world, to anything in the physical world that has an oscillator. Anything that you ever thought you could describe with cosine omega t plus phi, you could just as easily, and not just as easily, often more conveniently and more powerfully, you could describe with e to the I omega t. Like we use imaginary numbers in the real world to describe oscillating systems. Whenever we want to describe oscillating systems by using our knowledge of exponential functions rather than our knowledge of sinusoidal functions, we can do that as long as we use complex numbers to do it. I'm going to go one more beat on this. Remember, part of the advantage of using cosines in the first place, is that they wiggle. But also, I keep saying, because we already have this knowledge of circles, like radians and stuff, and like angle, and how angles are the same in a circle regardless of how big the circle is. So we use that knowledge and we graft it onto cycles that frequencies of oscillators, there's things are constant regardless of how big the frequency of cycles of oscillators are constant regardless of how large the cycles are, right? We already have this circle math built in, so it's convenient to use cosines and sines from circles to describe the cycles of physical oscillators. Well, similarly, there are properties of exponentials. There are properties of exponentials that make them really easy and powerful to work with when discussing oscillators. And some of those properties, cosines and sines, don't in the same obvious way have. I mean, just super quick example. E to the A times E to the B is the same thing as e to the a plus b. I'm not saying you have to memorize that right now or like get too like upset of, bogged down in it. But just as a quick example, there's things that you learn in math that at the time seem completely irrelevant, or at least they did to me. Like things like e to the a plus b equals e to the a times e to the b. Well, things like that make discussion of multiple analysis of multiple oscillators really easy and straightforward when we choose to use exponentials instead of cosines. And we can do that if and only if we involve what you might call imaginary numbers. So to be really specific, oh yes, the yellow at the bottom of the page, to actually really answer Andy's question. I mean, I think this is Andy's question, and then I'll move on, is not only in PChem, you will see when you get to PChem, I believe. I mean, you'll definitely see these second order differential equations and these oscillators. I mean, I promise you'll see that and hopefully have more confidence and more comfort having seen it first in Physics 204. But second of all, I believe you will often solve those differential equations in PChem using complex exponentials rather than cosines and sines. It's a really good thing to know in advance. Exponentials with imaginary coefficients. Like that's a very real thing. Also, and you notice, I mean, it's to answer Annie's question, but it's not just to answer Annie's question because like here it is written in yellow at the bottom of the page, or yeah, in yellow at the bottom of the page. If you go on, any of you who ever go on in electrical engineering, like specifically electrical engineering, or have a background in electrical engineering, like it's huge. These complex exponentials is totally how people analyze circuits in electrical engineering, is with complex exponentials. Long story short, short story long, complex numbers are totally like practical. They are. They're not any less real than real numbers for what it's worth. Okay. Uh, Oh, and it all works. Okay, I'm last on the sidebar. And again, I'm saying all this partly because it's just too interesting. I mean, because I agree with Andy. Like, once you even mention this, once anybody even mentions to me, like, just what I'm trying to say is that we can capture wiggling phenomenons with functions that don't seem to wiggle at all, as long as we drive them with a complex number. Like, first of all, just mathematically, abstractly, I would never have seen that coming. That's like interesting. It almost makes me want to study math in a way that I didn't think that I did when I started all of this. But if you're going on at all in certain branches of physics, you need to know that, or science, you just need to know and be familiar with complex exponentials are solutions to the differential equations, particularly the differential equation that describes simple harmonic oscillation. And the reason it's all tied together is this mathematical discovery, which is so powerful and so important in STEM in general, called Euler's equivalence, where cosines and sines and exponentials and complex numbers are all intimately related and in one package. For here on in, always e to the I theta, or you could say e to the ix, is literally equal, like Euler proved this. It's literally equal to cosine of theta plus I sine theta. Or if you want to flip it around and you want to express cosines in terms of e's, then cosine of theta equals e to the I theta plus e to the negative I theta over 2, where sine of theta equals e to the I theta minus e to the negative I theta over 2i. Like, that's all just like three different ways of saying the same thing, basically. It's just saying you can't. And if any of you have ever, okay, I'm really going to go on a second. I mean, math is cool. Can I just, like, math is cool. Okay. I'm sorry. It's just like cool. And did I always think that? No, just so you know. But I do now. So if you've ever thought math was cool, or have ever like read or like whatever, seen any kind of pop math stuff, or ever watched any videos by those guys, Three Brown, One Blue, and boy, this is not a paid advertisement, but boy, do I recommend. They're amazing. The YouTube channel, Three Brown, One Blue. I mean, they're such well produced, such visually captivating videos that explain like any. They're like Khan Academy for when you don't have to take an exam and when you really want to know and you really just want to be blown away by the beauty of math. It's like they have for every single topic they have. So anyway, like if you've ever watched any of those or heard of the concept that like e to the pi I equals -1, which is like a staggering math result that where four of the most important simple concepts of four totally different branches of mathematics are all put together in one equation. I'm just saying it. E to the pi I literally equals, oh, I mean, -1 equals 0, or however you want to say it, or equals +1. That comes from all of this. If you've ever heard of that, and if not, it doesn't matter. But that's all this. Um, okay. But physics. Back to physics now. The reason, and then also, oh my God, what time is it? Okay. The reason, back to physics. Remember, the point is feedback. The point is feedback. Even in something that's just going back and forth and back and forth and back and forth, there is a feedback phenomenon here. There, and by feedback, I mean when not only does input generate output, but output circles back and generates more input. That's what I mean by feedback. When input generates output and output generates input, right? Or put more mathematically, when the rate of change of a function is somehow determined by the function itself. That is feedback. And if you think about it, think in steps of 4 with the function sine or equivalently cosine, right? If the function itself is sine, if you take 4 derivative steps of it, you eventually get back to, you literally get back to exactly sine itself, right? I mean, first derivative is cosine, second derivative is negative sine, third derivative is negative cosine, fourth derivative, I mean, you see what I'm, yeah, fourth derivative brings you back to the original function itself, sine. Now, same thing with e to the x. E to the x, you don't have to take as many steps. You could do it in one step, but nonetheless, if you take 4 steps with e to the x, you will get back to e to the x, right? Derivative of e to the x is e to the x. Second derivative is e to the x, blah, 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 all the way. You get back to e to the x. Now, so in 4 steps, either one will get you back to the same place. I'm not saying it's the minimum. I'm just saying it is possible to do it in 4 steps. Well, look at I. Same thing with I. I mean, in terms of powers of I, if we treat I as a constant in a function on which we are performing the chain rule, I to the 0 is 1. I mean, anything to the 0 is 1, right? I to the 1 is I. I to the 2, I squared, is -1 by definition. I to the 3, I'm sure you remember this or you've seen this before. I to the 3 power is I to the first power times I to the second power. That means I times -1, i.e. negative I, right? But then that means that I to the fourth, well, is that times I. Or in other words, I squared times I squared. I to the fourth is -1 times -1 is 1. You get back to I to the 0. Do you see what I'm saying? I'm saying that all these, there's something intimate going on underneath the surface between sines, cosines, exponentials, and complex, is that all of them cycle in stages of 4 back to themselves. So that it's not a total surprise or totally out of nowhere that if you package them together, they can describe harmonically oscillating systems. Okay, now, oh, sorry. 3 blue, 1 brown. Yes, I always do that. Yeah, 3 blue, 1 brown, not 3 brown, 1 blue. I can't imagine what that would be. Yes, thank you. Good point. And put that into respectfully corrected portal, please. All right, now, did I just go off on a little bit of a like a thing? Yeah, sort of. What do you need to know for this class? What do you need to know for this class? You need to know for this class how to test any like for the exam, which we're not having yet, but when we do, what you need to do is you need to recognize that differential equation for simple harmonic oscillation. And given any function that anybody asks you to test, you should be able to test any function and see whether it does satisfy the differential equation and thereby describe harmonic oscillation. That you should be able to do for anything. You should understand conceptually why we could describe oscillators with complex exponential functions, like that is within your realm to be able to discuss or analyze. But you should also know that going forth from now on in this particular class, we're going to keep using cosines. We're not going to really use sines. We're not going to really use exponentials. Like you might be asked questions about them, but when we're doing labs or this or that, we keep on using cosine because it's good enough for our purpose. And we want whatever is most convenient for our purpose, always as physicists. So I'm going to move on to the part two of the homework where it asks you to keep sort of practicing cosines because cosines is how we're doing it. Um, so on so I'm gonna do another quick, really quick screen. Well, no, I don't have to. So part two of homework. So what I'm trying to do now, we have 25 minutes left. Um, I'm going to just blast through like answers. So it's up to you guys. Sorry, it's up to you guys to. I want you to check with your own personal homework. Um, and like see if these answers are okay to you. And if they're not, you should ask a question or point out or direct chat or something. Because basically part two of homework two is just meant to practice cosines and particularly now to practice how they work once a phase constant is thrown in. Okay. So um it's just practice. Therefore, I'm just saying that the answers are here on the board. I didn't, you have to show me the work to get the grade, but I'm just showing you the answer. So you should check. If you don't like any of these answers or understand them, please let me know right now. Um, uh, the one thing I'll say is when you get down to part B, number 8, the reason I wrote it in yellow is because I would think the answer that many of us would get, and I hope you're looking at your own answers right now, but when you get to 8 of part B, many of you may have gotten the answer t equals -1/4. If you did, then you did definitely know what you're doing and you're cool and everybody loves everybody. If you got -1/4 for t for the thing that I did in yellow. But I'm just saying as a physicist, like t equals -4th would mean 1/4 of a second before you started your stopwatch. Like, I mean, it means something. It's not meaningless. It means a quarter of a second before you started collecting data in your experiment. So, as a physicist, that's a little hard for us to access that data that was there before we started collecting it. Right. So I don't really think so if you're with me as a physicist, I don't think we're really looking for negative answers for time here. I would be more comfortable finding the first possible positive value for time, i.e., the first time in the experiment that the oscillator reached whatever it was asking. I think it was asking whenever it reached a value of um, that x equals 4 or x equals 0. What did it ask? Hold on. Uh, yeah, it said find a value of t for which x equals 4, or maybe it should have even said, a low value of t, whatever. So negative values would answer the question, and I don't think I would take off points on the homework. But if we're trying to get a grasp of how to picture this, I was looking for a positive value, so I did the work out, and I got t equals 7/4. Notice though, and someone said this in the other class very, very cleverly, like if you got -1/4 then notice that my answer is 7/4. If it seems obscure to you, that's really 8/4 ahead of your answer, right? 8/4 is in 2, as in 2 pi, right? I'm basically I'm just waiting a full period after your answer until data starts getting collected, until I get into the positive realms of t. So I got 7/4. If you got -1/4, I got 7/4. I don't think that's a coincidence. I think it's a full cycle later, and I just prefer it because it's a positive value. Okay, and then I got t equals 0 for the final answer. So those are my answers for that. I'm looking in the chat. So if there's any moving, going once, going twice, those are the answers. Okay. Then now, total shift here. Like what I really want to get to is waves and all that, but just so that we can put homework 2 to bed. Homework 2 was like long and had all these like math tools that you need to know for physics. And the main math tool thus far was like how to recognize and solve for the differential equation describing harmonic oscillation. But then there's this other math tool that almost has nothing to do with that, or seems like this other thing that came up when we were first physically analyzing the oscillator and thinking about work and energy. And when we were thinking about energy conservation and energy gets transferred when we do work, and we discussed that work is the path integral of force, right? Work is the integral of the dot product of the force vector with the displacement vector. Like we said, we have notes from one day where we made a big deal of like when you're computing work, you're computing a certain kind of product between two vectors. You're computing the scalar product between two vectors. You're asking what happens when you multiply two vectors in order to get a non-vector answer. Um, so that's a tool of math. That's a mathematical kind of operation that doesn't directly have to do with this, but is something we need for this class. So, so I'm going to shift. So I'm going to shift the screen again. Hang on one second. Right. So if we go to this next part, right? So again, I'm just saying this is unrelated in a way, but it's just another math tool that we need. And I just want to keep everything organized and linear and like finish homework 2 before we go to homework 3. So therefore, in that spirit, um, it asks you a bunch of questions here about vector multiplication. And yes, it's all coming from a context. Well, it's heading toward a different context, but it's coming from a context of work and energy. But up in the top right, where it says assume A, B cosine theta, blah, 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 I want to make it clear that assumption that it's giving you is pretty much all that you need to assume or to use in order to answer all these questions. Just like when it said I equals square root of -1, that's like all you need to do that other thing, those derivatives. So this is pretty much all you need except for one detail that will be the punchline of today's class. Notice. So I will give you I'll give you the answers in a second, but that's another screen share. So bear with me for a second. When you look at that where it says assume, can I do this? Can I wait? I forget. Can I? Yeah, like I am here. Okay. Where it says assume. Okay. The dot product of vector A and vector B literally equals the length of vector A times the length of vector B times the cosine of the angle between them. Now, again, this we discussed before, but let me remind you, this is like an explicit definition, and I think it makes sense. It's saying a couple things at once. Number one, it's saying that that this type of product of two vectors yields a non-vector. It like the length of A times the length of B times the cosine of the angle between them literally is a number, as it should be. And it's a number because the scalar and it's a number that is generated by the cosine of the angle because when we're computing the dot product between two vectors, like when we're looking at how much work you do on a box when you push the box at an angle, but the box moves horizontally, like let's say, what you're really asking is how much you're asking force times displacement, but you're really asking to multiply the component of force that is aligned with the displacement, right? When you multiply a dot product, when you do a dot product, you're looking at how parallel the two vectors are. Or put another way, you're only multiplying the components of the two vectors that are parallel with each other. And thereby, and that's why you're looking at cosine, because the cosine of 0 is 1, and the cosine of 90 degrees is 0. So the closer the two vectors are to each other, the closer the angle is to 0, the bigger cosine we get. So you are measuring the extent to which we can treat these two vectors as though they were just numbers on a number line. When you do, and again, honestly, 3 blue, 1 brown is awesome on this topic. Just to say, when you do a dot product, you are measuring the extent to which two vectors could be treated as two numbers on the same number line. And what you get is a number on the number line. Like, do you see what I'm saying? Like, it's not a coincidence that dot product, the scalar product of two vectors, measures parallelism, therefore uses the cosine, therefore produces a pure number. That's the dot product. We've used it in physics already to calculate work, but we're now, as a math thing, math tool, we're introducing its counterpart. In contrast, this thing called the cross product, which takes two vectors and multiplies them in a way that produces a vector. That's the point here, okay? And when you look at two vectors and produce a vector, now you're looking at the extent to which direction actually matters. You're preserving direction in your final answer. You're tracking the role that direction is playing in the computation. So now, first of all, use sine, not cosine, because now the more perpendicular the two vectors are, the more they differ in direction, the more of a role direction is playing in their relationship, and the bigger the sine of the angle is, right? The sine of 0 is 0, sine of 90 degrees is 1. So now notice, so on the one hand, what goes with cross product is sine, not cosine. But please notice this one other thing I have to say, and then I will move on, which I always say, and then I never do. Notice that it doesn't just say it doesn't just say A cross B equals AB sine theta. Like, it's not as simple as the notation right above it. And this is not a typo either. I just want to see, wait, can I do a highlighter or a thing? Sorry. Like, no, that's not right. Okay, okay. Well, I'm just saying, like, please notice this, right? What's up with that? Those double absolute value symbols they are double absolute value symbols. What do they really mean? What they mean is the magnitude of a vector. If you think about it, absolute value in the first place means how far something is from zero, right? Like, the absolute value of -7 is 7, because what we're really asking when we ask the absolute value of 7 is we're picturing a number line, and we're saying, like, how far away from zero is -7? Oh, it's just exactly as far as the number 7 is. Like, it's 7 units away if I don't care about direct, right? That's what absolute value means. So when you ask the magnitude of a vector, you're doing the same thing. You're drawing an arrow out from the origin, but now in any direction you want, not necessarily along just one axis, but anywhere in the plane. And when you ask the magnitude of a vector, you're just expanding that idea or extending that idea and saying, how far away does the vector bring us from zero? So double absolute value symbols is what we use to mean the magnitude of some vector, even if, like, a vector that could be in 2 or 3 dimensions. So why I had to throw them in there on the sheet is not just to be, is to say, wait a second. The length of the vector A times the length of the vector B times the sine of the angle between them, what that is a number. AB sine theta is a number. That will be the magnitude of the final answer produced by a cross product. But it's not the whole answer. It's the magnitude of the whole answer. The whole answer produced by a cross product had better be a vector. That's the point of the cross product. It is looking at direction and spitting out an answer that has direction. So the one thing that is not clear yet from that little sidebar at the top of the sheet, what it's telling you is literally what the dot product is always equal to, and then it's telling you what the magnitude of the cross product is always equal to. It does not yet say what is the direction of the cross product always equal to. We need to figure that out or say something about that within the next 12 minutes before the class is over, okay? But I want you to I want it to be clear, like, there's a piece of information yet to be produced. And I didn't have to do it with the dot product, because the dot product by definition produces a number, not a vector. Okay, that said, I'm going to switch the screens again, go back to some answers here. I'm going to switch the screens again and go back to some answers. Right, so I'm going to switch the screen. Right. Yeah, that's what you need. You need two of me. You definitely need that. That's what my wife wants. Okay. All right. So wait, hello, hello. Okay. So All right, so here are the answers, or here are the answers to part three. So first in one and two, like first it asks you just to like rank the results of the dot products from greatest to smallest, and then rank the results of the cross product from greatest to smallest. And you again stop me if you can't read one of these answers or you don't agree or you don't understand. But the rankings are coming from just the idea that dot products measure parallelism. So the closer the angle is to zero, the greater the dot product, right? And that I can do that assuming that all the lengths are given as the same number, which I think they are here. I think they're given as the number three. Um, and then same thing with the cross product. The closer the angle is to 90 degrees, the more the two vectors differ in direction and the more the bigger the cross product is. So those are my answers. I think A dot B is greater than B dot C, which is greater than A dot C, which is greater than A dot D. And conversely, I think A cross D is greater than A cross C, which is greater than A cross B, which is greater than A cross F. Those are my answers. I'm looking for a little now the wrong. Okay, I'm looking at the chat. There's no questions. You can still ask questions. Please ask questions. Don't be intimidated by the fact that I'm going on. Please. Now it goes to three. This is where we have 9 minutes. Three, it asks you to do various different dot products and cross products, assuming that the vectors have lengths, the given vectors have lengths of three. So like I did the answers, so each time I'm either doing like vector length one times vector length two times cosine of the angle between them, or I'm doing a sine of the angle between them. But I'm doing these answers, but then notice when I get to D and E, I put question marks there. Uh, not because I'm doubting myself, not because I'm not sure, but because I think there's information that is not yet, like I'm not done with my answers to D and E. If I look at, and we have 8 minutes left, when I look at D and E, those are cross products. Well, and so is like G or a couple others, but those are cross products that produce non-zero answers. So I want to emphasize again, cross product is supposed to produce a vector. So it is not sufficient. It's not a complete answer just to put a number as the answer. It's got to be a vector pointing in some kind of direction whose length is that number. So that means, so by the way, if you did that for your homework, if you did all of this and showed work and did the 5-step method and showed pictures and did all this, then that's what I expect you to do. Like that's all you could do that's all I could want you to do based on what was written on the homework sheet. But now let me push it a step further. And again, please do understand, I'm about to teach you something or start teaching something that does not directly yet relate to cosines or anything like that. It's just another math tool that we need. Of course, it all eventually relates, but so the question that is raised by D and E, the question that is raised that we now need to answer, even if you got 100% on the homework, or even if you do get 100, the question is, what if the cross product produces a vector? How do you know the direction of the vector? Direction, right? So yeah. So let me put it in slightly more formal terms. Let C from here on, or just like for right now, let's say you cross two vectors, A and B, and let's say we're going to call the answer C. And in fact, let me be more specific. Say like here's vector A, some arbitrary vector A, and here's some arbitrary vector B. So like they have different directions and they have different lengths, and we're finding out their cross product. Well, their cross product, let's call some vector C. What we know is that the length of that resulting vector C is going to be the length of A times the length of B times the sine of theta for the reasons I've already explained. That the magnitude of that answer is going to indicate or measure how perpendicular the two vectors are, how much direction is playing a role in their relationship. But the question is, what's the direction of this answer C? And the way we can put that is with this notation called a unit vector. Well, the hint is, so I'm going to tell you, I'm not asking you, I'm about to tell you, but it's like a little bit funny. So hang with me for 6 minutes. Um, the big important feature here to repeat is that the cross product is producing a vector that is meant to indicate how perpendicular two vectors are, the extent to which two vectors are perpendicular with each other. So the answer to the cross product does turn out to be always perpendicular to each of or to both of the original vectors being crossed. Like, that's not my full answer yet, but let me first start by saying, if you're looking at how perpendicular A is to B, the answer that you get will be a vector that is perpendicular to A and perpendicular to B. How, I mean, is there such a vector? And why is that, by the way? Because we have five. Why? Well, a big reason is because if the operation is to be fair, if it's to be an operation that treats each vector with sort of equal weight, then it actually kind of stands to reason that our answer should not be any more angularly related to one of the vectors than the other. It shouldn't be at an angle that's like closer to one vector than the other necessarily. Just like when you do in with numbers 2 times 3, you don't do 2 squared times 3 or 2 times or even 2 plus 3. You don't do 2 plus 3 to the fourth power. You don't put more weight on one of the numbers than the other. So we don't want to, so if we're looking at the way these two vectors are directionally related, we don't want to put more weight in the operation to one of their directions than the other. So our answer, to like be fair in this sense, our answer will be just as far angularly from one as it is from the other. Our answer will be always 90 degrees from each of the original vectors. Now, how is that even possible? Can you even picture a vector that is 90 degrees from both A and B? Well, I can't unless I'm willing to pop out of the plane in which A and B are drawn. If you picture an arrow that pops out of your screen or your piece of paper or points into your screen, then that arrow will necessarily be perpendicular both to A and to B. And that is what the cross product answer will be. The vector that is produced by crossing A with B will be a vector that either pops out of the plane of A and B or pops into the plane of A and B. The only question is which one? Is it out of the plane or into the plane? Good question. Well, what would happen if you made the wrong choice? You'd be off by a negative sign. Like the real answer is the answer could pop out or in. It just depends on what you want to call positive, right? It totally depends on what you want to call positive. Oh my God, sorry. It totally depends on what you want to designate as positive. That's a matter of convention. But there's a convention that we all follow, we all agree on. And the convention is called the right hand rule. What you do, so here's the answer. The answer to the cross product, and there's 2 minutes, is always given the direction of the vector produced by crossing two vectors is always determined by the right hand rule. And if you've ever heard of the right hand rule ever in eighth grade, in 10th grade, in some magnetism section of physics or something, the APB physics exam, whatever, if you've ever heard of any kind of right hand rule, all the right hand rules that you've ever learned that were out of nowhere are all just derivations or variations on this exact mathematical convention. Hold on. Right. So, right. Oh, good question. Good question. Hold on. I may or may not get to that. 1 second. I see it. 1 second. Let me just say what you do to do the right hand rule is you place your fingers along A, the first vector that you're multiplying. You place your, well, sorry, you place your, I can't, you place your fingertips on A. I can't. You place your fingers of your right hand along A and you curl them toward B. And wherever your thumb points, that which is necessarily perpendicular to plane, the thumb will either go into the plane or out. If the thumb goes into the plane, we draw an X, which it did in this case. I curled my fingers from A to B, my thumb pointed into the plane. I draw an X because I'm picturing my thumb as a little vector arrow flying away from me. And all I would see is the cross section of the tail feathers in the back. If it were coming out, I would draw a circle. I mean, I would draw a dot because all I would see is the tip of the arrow coming toward my eye. So that's the answer to the chat question. If it's going in, well, there's more to be said about it tomorrow, but that's the main answer right now. If it's going into the plane, I draw an X. If it's coming out, I draw a dot. And so the answer to this one is going into the plane, and you can indicate it like that. Um, So the right-hand rule is the convention for telling you whether the answer goes in or out. In other words, then the opposite you'll notice will be negative. So well, I'll leave it at that. So yeah, so if you do vector B cross into A, if you put your fingers on B and you curl them up to A, then your thumb would point out. So A cross B equals the negative of B cross A. It's an anti-commutative relationship. But what you need to know now is the magnitude of the cross product is vector length times sine of the angle between them. And the direction of the cross product is determined by the right-hand rule, a convention for ensuring consistency of positive sign whenever we find vectors that are that are perpendicular to the plane in which two original vectors are drawn. Okay, that's 420. So have a great. I'll see you Wednesday. And wait, okay. So maybe I didn't answer Andy's question, but you can go. I mean, unless Andy, if you want me to answer that more deeply, I will. But I'll see you. I'm stopping the recording. Have a nice day.